So folks, both local and in other states and places, it is our pleasure today afternoon to have Professor Jason Marden from the University of Colorado at Boulder speaking to us. Jason has been very active in the area of game theory in general. He got his PhD from the University of California at Los Angeles, postdoc at Caltech, and started at UC Boulder, CU Boulder rather, very recently. He has got several awards, including very recently the AFOSR Young Investigator Award. And so we will now hand over to Jason. Let's start from Jason.
Well, thank you, Srinivas, for the kind introduction, and it's actually a pleasure to be here today. So the talk that I'm going to talk about today is game design for distributed optimization, and this is joint work with a graduate student over at Caltech, Nali, and so hold on one sec. For some reason, it won't go. So apparently, well, okay. So the keyboards won't, the keys won't work, but apparently the mouse will. So if this gives problems down the road, we'll have to do some form of a reset, but hopefully it'll go forward. So there's a picture of Nali. So once again, she's a student in CDS. She's graduating this coming year, so she's going to be an ideal job market candidate. So I don't know if A&M has any positions available, but if you do, I can't give any higher recommendation to a graduate student than I can to her. So she's responsible for all the results kind of in this talk. So basically, the general theme of cooperative control is this idea of deriving desirable behaviors through local control algorithms. And several different applications have I guess, fueled this interest in cooperative control. You know, starting with the far left, we have this idea of sensor coverage. Francesco Bullo has been a major player in this arena. And so the general idea is here I'd like to establish some form of a local control algorithm. Here, local, and so that each individual sensor itself is making its own decision in response to local information. So I'd like to establish a series of local controllers such that the global behavior will be desirable. So here, for example, in the sensor coverage is maybe you want to spread the sensors out to maximize coverage area. Maybe you want to minimize the amount of time it takes to detect a catastrophic event. There's numerous potential global objectives, and the idea is we want to reach those global objectives or satisfy those global objectives using the local controllers. You know, network coding is another one, and Srinivas has done some work in this domain as well. Here, I'm just trying to route information through a network in some fashion to minimize some degree of cost. And network coding deals with some degree of information of what I'm allowed to, how I'm allowed to potentially package information together to save on cost. And the general idea here is networks can be quite large. There can be many users trying to utilize this network. It seems unfeasible for centralized control, meaning one individual control entity to route all units of traffic over the network at all points of time. Rather, decisions need to be locally in response to local information. Wind farms are another one, and where once again is the objective here is to maximize power capture out of the wind farm. The goal here is to attain those performance guarantees through the use of individual wind turbine control algorithms. So, you know, going through the applications above, there's several appeals in transitioning from centralized to decentralized decision making. These appeals obviously mean that, you know, for example, you know, local processing. Now, you know, decision making is made at the local level. And so what does this mean? That means decision making is potentially more manageable. It's not as complex. We don't have to solve such a large scale optimization problem. Rather, things become smaller in scale. It reduces the need for communication because we don't have one central authority talking to everyone at all at the time. And in some sense, it adds a degree of robustness into the system. And the standpoint is, you know, in a centralized communication scheme or a centralized control scheme, if the communication system fails, then all of a sudden, you know, the agents don't know what to do. So here, you know, introducing these local control laws introduces this robustness automatically. So there's obviously several challenges that come up. Number one is, you know, when you have several agents, potentially thousands of agents, each making decisions locally in response to local information, is it even possible to characterize on a global perspective what's likely to emerge? If it is it possible to coordinate? And then we also know that you know, whenever we take a centralized optimization problem and break it up into bite-sized pieces, we induce a degree of inefficiency into our system. Is it possible to characterize how bad or that inefficiency is? So the considerations that we're thinking of, regardless of whether we're in sensor coverage, network coding, or wind farms, is we have some global objective. It's either static or objective. We have some form of admissible control space. This admissible control space could be related to what are our operational limitations. So, for example, what are the individual sensors capable to do? or what information do they have access to. So, for example, it's you know, a control policy is dependent upon what information agents have access to. Different levels of information instead gives us different classes of admissible control policies. So we have some degree of an admissible control space, and we want a degree of robustness, meaning that we'd like our system to perform well even in environmental uncertainties. And we'll more formally define these as we go along. But in general, it's just thinking about the sensor coverage, but one can map this to any of the other problems as well, is we have some global objective that we're going to seek to minimize. Here, that global objective is captured by capital C. And we want to minimize it over certain variables, and those variables are V1, V2, V3, all the way to Vn, where we're going to think of V1 as the decision of agent 1, V2 as the decision of agent 2, and vice versa. And we'd like to optimize this performance objective subject to admissible control policies. And here I'm going to write admissible control policies in this form. The decision of agent I at time t is somehow dependent upon the information that agent I has access to at time t. Okay? So here the information that agent I has access to at time t is our constraints on our admissible policies. So for example, in the sensor coverage case, it could be that an individual sensor has access to information regarding neighboring sensors, to neighboring environment, but not the whole thing, and not the whole environment at large. And this, in essence, puts the constraints on the admissible control policies that we're going to consider. So if you think about it in the literature, there's two main ways of trying to transition from a global objective that I'm trying to minimize to the derivation of admissible control policies. And I'm going to call these as algorithm design and objective design, and I'll try and highlight how they're different before or as we proceed. So first, in terms of algorithm design, so what algorithm design is we feed in some form of an objective C, and we turn a crank, and out of this crank comes the policies. So it's a systematic procedure for how to take any form of a global objective policy and come out of it local agent objective functions, or let's just call it agent control policies. And so here are some of the common approaches to this are gradient descent, subgradient descent, incremental subgradients, consensus-based subgradients, and many more. And there's a list of these type of algorithms of, once again, how to translate a global objective C to get admissible control policies or control policies pi. So when doing this, one needs to ask the following question. If we have admissibility constraints, do these cranks, whether it's gradient descent, subgradient descent, do these constraints yield admissible control policies? I mean, do they satisfy the information and operational constraints that our given system has embedded into it? Does it necessarily guarantee convergence to maybe an optimizer or an efficient solution of our global objective C? And one can ask, well, is it robust? And meaning, if rather than following the specific control policy, rather we looked at cases where there may be delays in information or inaccuracies in information, asynchronous clock writes, you name it, do we still guarantee the convergence guarantees that we had before, that we would like? So just to motivate this question, let's just look at a simple example. So here we have three variables, V1, V2, V3, and we have a simple quadratic cost function that we're trying to optimize. The values of V, P, and Q, or P and Q are listed above. But imagine that we have a degree of admissibility constraints, which is highlighted by this graph. So here the admissibility constraints are as follows, is agent 1 only has access to information about agent 2. So agent 1 does not have information about agent 3. Agent 2 has information about both agent 1 and agent 2. And likewise, information 3 only has information about agent 2. So both agent 1 and 3 do not have complete information regarding the system as a whole. Agent 1 is missing information about agent 3. Likewise, agent 3 is missing information about agent 1. And what does missing mean? Missing means that, in some sense, the admissible control policies that we'd be searching for in this realm, agent 1's control policy can't depend on the true state of agent 3, and vice versa for agent 3. So if we wanted to look at a common approach to how to tackle such problems, gradient descent comes to be one of the most common ones out there. And so here, what we could say is that each agent follows their control policies. Each agent acts in accordance to the gradient of the objective with respect to their local variable. So here, the gradient of the cost function with respect to V1 takes on that form, and the gradient of the cost function with respect to V2 takes on that form. And so what do we know by doing this? We know that, well, this will obviously converge to the optimal, to the minimizer of our quadratic cost function. However, it doesn't satisfy the locality constraints that we have. Okay, so it's not necessarily local. meaning that in order to implement this control strategy and implement a gradient descent process, agent 1 needs to have access to V3. Likewise, agent 3 needs to have access to V1, which is not satisfied in our setting.
Jason, you can use your mouse to point.
My mouse isn't showing up on top of the screen.
Oh,
so
you can see it.
I could point with my finger, but that wouldn't come across either.
Okay.
So so feel free to, whenever anyone asks a question, I'll just escape out of this so that I can see you guys, and then I can highlight if there's any inaccuracies. So that's what I'm calling algorithm design. So once again, what was that? That was a systematic crank of how to translate our global objective C to local agent, or to policies pi I, and then we had to ask the question after the fact is, was it admissible? Okay. So a secondary point of view, or a secondary way of thinking about designing local agent control policies is the idea of doing objective design. And so what do I mean by this? I mean introducing an intermediate step between the global objective and the agent control policies, where I design local agent control, or local agent objective functions, which I call J1 through Jn. Okay? So these local agent control policies could be the same as the centralized. So they could be set at C. So J1 could equal C, J2 could equal C, J3 could equal C, or they could be chosen as something different. And the idea is what we want to do is show that potentially we can explore this flexibility by allowing us to design agent objective functions differently than C to try and overcome some of these issues that we saw with just the standard gradient descent process. So the general theme of what we're thinking about here is, well, maybe what we could do is whatever admissibility and operational constraints that we have, we could just directly embed them into the agent cost functions, or the agent objective functions J1 through Jn, and then have these individual agent objective functions serve as the target functions for agent control policy. So think about this as what we're going to do is we're going to remove from each agent having access to C, and now each agent only has access to J1. They operate thinking that this is the true system cost, but it need not be. Okay. So here one can ask the following questions that we were asking before. Is it robust? Is it converge? Is it admissible? And here convergence takes on, potentially a more significant, is more challenging than before. Because now once again, we could potentially have n different agents responding to n different objective functions. Okay. So somehow it got messed up. So back to our example before, once again, is how we could have proceeded with this is, once again, is embed these locality constraints into our objective functions. What does that mean is maybe I could have assigned agent 1 an objective function that only depended on V1 and V2, agent 2 an objective function that depended on everyone, and agent 3 an objective function that only depended on V2 and V3. So once again, here the true system cost depends on everything, but maybe what I could have done is utilize the structure that game theory provides maybe to assign objective functions with this form. So what do we know is that if each agent performed a gradient to this local objective as opposed to the true, this would satisfy our locality constraints. We would get that for free. But now all of a sudden the question of convergence, would it converge and where would it converge, become more challenging issues, because we have to address the fact that agents are responding to heterogeneous forms of objective functions. Okay. So, sorry. Am I going backwards or forwards? So, let me try this again. Okay, now it works. Okay. So once again, so the idea is behind this whole thing is well, in many cases that algorithm design could be thought of as the realization of an objective with some form of a gradient process attached to it. But is there any form of a fundamental difference between thinking about one as opposed to the other, right? Both of them yield agent control policies. Is there any reason why we should pursue the derivation of such policies by actually formally introducing objective functions at an intermediate step? And so I'm going to argue that we do have a reason, or there is significant reasons to introduce this intermediate step to think of objective design. And so one of them is this idea of a modularized design architecture. So what does this mean? It means that, well, if we design the objective functions properly, and we'll define or we'll talk what properly means, it's that the actual learning algorithm, how agents seek to go about updating their objective functions, which yields us our policies, we could have that for free with automatic guarantees. Okay? And there's already several forms of learning algorithms out there that we could utilize. Okay? So once again, for example, if I can design the individual agent objective function so that the resulting game is a potential game, and we'll define what potential game is later, then any learning algorithm for potential games could be used to drive my behavior, to drive the behavior, or to derive agent control policies that guarantee convergence to some form of an equilibrium. Okay. But possibly the most important reason to delve in this route is this idea of automatic robustness guarantees. So when someone specifies an algorithm, and there's many different algorithms out there, so what this algorithm is how does an agent make a decision at time t+1 given information that it has? Well, if we follow that algorithm, we may get convergence to, usually the typical thing is if you follow this algorithm, you'll get convergence somewhere. The natural question is, well, what if we can't exactly follow that algorithm? Do we attain convergence? What can we say about where we're going to go? And in many cases, it's hard to say. Sometimes these algorithms are extremely difficult to the point where characterizing the robustness is challenging. Well, here, one of the nice things about it, and I'll use this framework of potential games again, is the framework of potential games is inherently robust. And what do I mean by that? I mean virtually any learning algorithm that you throw at it. And what I mean by learning algorithm, any learning algorithm where agents try and improve or try and optimize their utility function or cost function will in some sense guarantee convergence to an equilibrium. So what does that mean in systems where behavior is corrupted by any number of issues, right? Getting to a Nash equilibrium potential game seems relatively easy. And we'll elaborate a little bit on that as we go forward. Okay, so the question that we're going to address in this talk is if we start off with a global objective, is how do we design agent objective functions? And so if we thought about this from the social sciences or from the engineering systems, the motivation for asking this question would be different, the tools would be different, but the general theme would be the same. So in social systems, one could ask this question, if I had freedom to design agent objective functions either through taxation or other means, I'm interested here in focusing on stabilizing efficient outcomes, whatever efficient in some sense means is tied to the application domain. In engineering systems, I'm focusing on dynamics that converge to an efficient outcome. And so these are very well tied, but these different agendas require in some sense, new developments. Okay. So once again, the goal of this talk is to develop an underlying theory for utility design. Here we're going to talk about constrained utility functions. We're going to be talking about efficiency of Nash equilibrium with respect to the system level objective function. And we'd like the game to possess some form of desirable structure. So once again, the three objectives that we're going to consider is we have information constraints. Those information constraints define the set of utility functions that we could potentially define. So for example, back to the example that we dealt with is, the objective or the cost function of agent 1 can only depend on information regarding D1, D2. We would like to design utility functions in such a way that a Nash equilibrium exists and is efficient with respect to the system level objective. And we'd also like to ensure that the game possesses a desirable structure, such as potential games. And here what I mean by desirable structure is that it can be exploited in distributed learning. So we can apply distributed learning algorithms that guarantee convergence to an equilibrium. Okay? Note that if we're able to do this, this gives us a control policy which will converge to some form of a Nash equilibrium. If we know that it's efficient, then we're in business. Okay, so the question that we can ask is, well, is the framework of strategic form games, the classical game theoretic framework, rich enough to satisfy this goal? And it turns out that the answer is no. And so we'll delve into this, we'll delve into why the answer is no via a counterexample. But before, I just want to focus just a little bit more on this question, is that why strategic form games may be the logical choice to analyze social systems, whether or not it's the right choice to design distributed engineering systems is a different question. And so much of the work in game theoretic cooperative control has sought to utilize this framework. Recent work now from a variety of people is starting to analyze it, well, is this framework rich enough to conquer our needs? If it's not, then we should redefine the framework in a rich enough manner, but to conquer the challenges that we're after. So here the answer to this question is no, and I want to kind of show why this answer is no using an example. So to use this example, I'm just going to use it the classical average consensus problem. And so here's an illustration of a network. And so here the yellow dots represent the individual agents, and the blue lines indicate is who are they connected to, meaning what information do they have access to. So if a blue line is connected between two yellow dots, that means that those two agents have that agent has access to the other guy's information. Okay. So the setup here is we have a player set, which we're going to note as capital N. The information set is just capital NI, which is somewhere in N. So it's a set of agents that I'm connected to in this network. Each agent has a set of values, and we'll call those set of values VI. So just imagine that could be the entire real numbers, and has an initial value VI naught. And the goal of this problem is to establish some form of a control algorithm, a local control algorithm, where agents only, where once again the decision of any agent at any instant of time is only dependent upon the information that he's access to. So in this case, the values of his neighbors. Okay, and the goal is to design such an algorithm such that all agents will reach consensus or will converge to the average of the initial values of all the agents. Okay. So we could formulate this as just a regular optimization problem. So here the system level objective is in the top left. We'd like to minimize this form of objective function, subject to the constraint that the sum of VI's is equal to the sum of VI naught. Okay. So that's just a formulation of the average consensus problem, but just writing it as a system level, writing it as an optimization problem. We're interested in solving this optimization problem using control laws of the following form. So here, the value of agent I at time t can only depend on information about neighboring agents at time t. So he doesn't have information to everyone, he just has information to a small collection of other agents. So here, what we have is in the system level objective, we have that such that the VI means that there's some degree of coupled constraint on the agent's control policy. And here, the fact that all the control policies just rely on information about their neighbor, that's our locality constraint. Okay, so once again, here's an example where here's the characterization of our objective function on the left. Here's the characterization of our constraints on the right. Okay. And so here could be one such goal. Well, maybe one game theoretic goal would be the following, is define local and scalable cost functions, and I'll define what that means, such that Nash equilibrium exists, and all Nash equilibrium minimize this objective function, minimize the objective function that we have up there on the top left. And what do I mean by scalable? Here's the notion of scalability that I'm looking at, is to say, well, maybe what we can do is apply a general form of utility functions that every agent has. So here, think about this as the cost function of agent I.
Sorry, can you motivate the system level objective for a second? The reason is, I mean, if you didn't have the coupled constraint, one way of achieving consensus is for everybody to pick the same value 0, right?
Right.
So what is your system, the constraint kind of modeling?
So one of the objectives that, or one of the issues, so one of the rationale between average consensus is the idea that I don't want to, we could imagine that we have several different sensors in the field, and they're all taking a measurement of something. We would like to get the average. Okay. Right? So it's not just good enough to come to consensus on any one sensor's measurement, with the idea that one sensor's measurements might be bad. But in some sense, getting the average could represent a better aggregate measurement. Okay. Right. So that's what motivates that constraint on the bottom. So the constraint on the bottom is nothing more than we want to get to the average of the values. So think about VI naught as their measurement of something, right? Which let's say takes on a real number, maybe between 0 and 1. And each sensor could be bad, so the measurement alone could not reveal a lot of information about the environment at large. But if we somehow did an aggregation, so we took an average, that might give us a better indication of what this measurement truly should be. Right. Does that answer the question?
Yes, thank you.
Okay. Okay, so here, this idea of scalable is this idea of that, well, maybe I can just apply a general form of utility function. So here, the cost function of agent I given a value I and d minus I, well, it's only going to be dependent upon two things. What are the values of his neighbors? What are the current values of his neighbors, which is Vj, j within Ni? And what are the initial values of his neighbors? And so this notion of scalable says I'm going to apply some general way of processing, of how to process your neighbor's current values and previous values into an objective function. And the idea is everyone's going to have the same processing method, meaning that I don't want to have to design different types of cost functions for different people in the network. Okay, so I want to remove the network component from it. Here's just a general cost function that I'm going to do. So I'm going to design a single f, and every agent is going to follow the same f. Okay, And so what I'd like to do is design a single F such that, once again, that a Nash equilibrium always exists, and any Nash equilibrium optimizes my system level objective there in the top left. Okay, and so what am I doing is I'm embedding, once again, and we talked about this admissible class of utility functions or objective functions that we're going to consider, is I'm embedding the locality constraints plus the scalability constraints directly into my agent's cost functions. Okay, and I'm looking over that class. Okay.
Why is it important that it be a Nash equilibrium?
So the only reason why it's important, it's not. So this is just one form of objective. So if I could ensure that Nash equilibrium coincided with the system level objective, or the optimizer of the system level objective, and that it was a potential game, then we have algorithms that get us there. If it's not a Nash equilibrium, then we potentially need to derive new algorithms to do this. So here we're trying to build upon the existing literature that already exists. Okay. So here's just one form of objective that we consider. Is it possible to do this, yes or no? And it turns out that the answer is no. Okay, it's impossible. And so let's look at a simple example to try and get at this. So here, think of two settings, setting 1 and setting 2. Setting 1 is over on the left. And so in this case, we have 3 agents that start off with an initial value of 0, and 1 agent that starts off with a value of 1. And the black arrows indicate the interaction graph or the informational constraints of our system. So in this case, the red guy knows information about the glass guy, the guy with glasses. The guy with glasses knows information about the red guy and the smirky guy, and vice versa. Okay. Setting 2, all that we did is we added a 5th agent, where now we have 4 agents at an average at the initial value of 0, and that we have 1 agent with the initial value of 1. So here the key is that the average of the two settings is different. The average of the setting on the left is 0.25. The average of the setting on the right is 0.2. And remember, our goal was to design a single F that would achieve this objective for any form of a realization of a network. Right? We wanted to abstract out the network dependence and just design a general way of proceeding that was scalable and that would guarantee these qualities for guarantee that a Nash equilibrium exists and is efficient for all potential realizations of the network. Okay. So what I want to do right now is focus in on this individual guy, the guy with glasses. And so what I'm going to argue is if the guy in glasses is ever satisfied on the left, both the guy with glasses and the guy with the green guy would be satisfied on the right. So note here that the guy with glasses on the left, he has the initial value of his neighbors is both 0. Okay. Now notice that both individuals on the right, the guy with glasses and the green guy, they both have 2 neighbors, and both their neighbors' initial value is 0. Okay. So what does this mean? Well, in some sense, they have the same initial conditions. Okay. So the initial values is not dependent. So all that is going to differentiate the objective function of one from the other is the current values. And so what does this mean? It means, well, if something is a Nash equilibrium of setting 1, it's also a Nash equilibrium of setting 2. And you can get this by just realizing or just by looking at the guy with glasses. If the guy with glasses doesn't have an incentive to deviate from V, given that everybody else is putting from V, then also in setting 2, the guy with glasses and the green guy, they also won't have an incentive to deviate from V as well. So what does this mean in some point? It means that, well, V, so everyone being at some value of V is a Nash equilibrium of setting 1 also implies that everybody being at V is a Nash equilibrium of setting 2. So where does the contradiction come from? It comes from the fact, well, you know, if V is 0.25 across the board, right, if that's a Nash equilibrium setting 1, that's not optimal in the case of setting 2, right? We know that the average is 0.2, so there's the contradiction. Okay, so but once again, think of this as merely a toy example that suggests that the objectives that we were trying to get at in terms of through a game theoretic design, we weren't able to achieve those objectives using the classic framework. Okay, and the details about this.
Hey, Jason, I have one question. So is it possible like these two V, like V in setting 1 is different from V in setting 2?
Okay. Right. No, but all that I'm claiming is if I know something about it, if I know V is a Nash equilibrium of setting 1, based on this, just using the fact that here's the structure of the utility functions or cost function that I'm considering, I can infer from that that it's also a Nash equilibrium of setting 2.
Yeah, but for the setting 2, it's impossible to get these v to be all equal to 0.25, right? Because the sum have to be equal to 1.
So once again, as we removed the sum out, we were asking the sum is an artifact of the optimization problem.
Oh, okay.
The sum was a constraint on our optimization problem. We were asking the question is, can we remove all these constraints? So not think about the algorithmic side that you were thinking where we keep this constant throughout the process. But could we just design cost functions that ensured the equivalence, that ensured that any Nash equilibrium was an optimal solution?
Yeah, but if you remove the constraint, then the VVVV is optimal solution for the problem, right? You also reach the consensus.
No, so that doesn't solve, so the optimal solution of the setting on the right is 0.2, 0.2, 0.2, 0.2, 0.2.
Right, with the constraint of the sum should equal to 1.
Right, exactly. So what this means is that if we design utility functions in this class, however you wanted to do it, it means that we can't ensure that all Nash equilibrium are optimal in both setting 1 and setting 2 simultaneously.
Okay.
Thank you. That's all that this shows. If something's a Nash equilibrium of 1, it's also a Nash equilibrium of 2. We know this does not represent an optimal solution of setting 2, and so hence this kind of shows the contradiction.
Okay. Thank you.
No problem. Okay. So once again, what does this kind of illuminate? This kind of illuminates we set off with an objective of what we wanted to do for cooperative control. We wanted to design utility functions within a certain class that ensured that all Nash equilibrium represented optimal solutions. And that example showed that the class that we identified, it was impossible to do that. Okay. So what are we going to do with this talk is, well, we're going to say, you know, this class of games is not rich enough to tackle the demands that we're going to do. So we're going to talk about introducing an underlying state space into the game environment. And what does this mean? This means kind of, in some sense, moving in the direction of Markov games, at least in an epsilon direction. And so in some sense, this complements a lot of recent work done in the game theoretic learning, where what's been going on is that the authors have been introducing a state space into the underlying dynamics to improve convergence guarantees. So for example, Peyton Young in 2010 introduced this auxiliary state variable which represented moods into a learning algorithm to derive an algorithm that converges to a pure Nash equilibrium in any game where one exists. So once again, what's the literature been seen over there is enriching the class of learning rules through the use of state variables to try and attain convergence in classes of games where convergence has not been proved before. Okay. So this kind of parallels this. We're going to talk about introducing the state, go into the utility functions. So once again, the outline of the talk is just to develop an underlying theory for tackling utility design. And once again, we're going to introduce an underlying state space into the game theoretic environment. So once again, normal form games, what do we have? We have a set of players, which is 1 through n. Each player has a set of actions, which is denoted as capital AI. And each agent has a cost function, which depends on not just my action, but also the action of everybody else. So here, capital A denotes the joint action set, which is the Cartesian product of the individual action sets. So that's the nominal setting. We showed that that nominal setting wasn't enough. And now we're going to transition to a state-based setting where we introduce an underlying state space into the game theoretic environment. So what does that mean? That means we have some state space X. We have some cost functions are now state dependent. So what does that mean? The cost of an individual, the objective function of agent I is dependent upon the joint action profile A, but also the state X. So we now have a state dependent cost function. And now we also have a state transitional probabilities, meaning that if we're at some state today and we make some action, we take some action today, this could generate a new state tomorrow, and that's captured by this state transition function P. Okay, so we'll formalize exactly what's going on in this, but at least the flavor is all that we're doing is we're going to talk about how to introduce an underlying state space into the system. And here the framework of Markov games is incredibly complex. We're going to view just a simplification of it where we focus on myopic players and static equilibrium concepts and really focusing on what would a potential game extension look like in this realm. And then part 2 is utilizing this enhanced framework is we're going to talk about, well, what can we do in terms of utility design to overcome the limitations that we saw with before. Okay, so that'll be the general field to talk. So as just preliminary, so once again, normal form games, we have players, actions, and cost agent utility or cost functions of that form. You know, here's the typical definition. Here's a Nash equilibrium, just any action profile, where we're at some point where each person is doing as good as they could if they would have switched to any other strategy. So in an action profile, A star is a pure Nash equilibrium. If the cost that I get for A star is as good as the cost I would get for any other action, provided everybody else stays fixed. And something that we're going to use throughout, or we're going to talk about it all, is this idea of a potential game. And a potential game is a normal form game where there's an additional structure placed on the agent utility functions. What's that structure? That structure says, well, there exists some form of a potential function which maps the joint action space to the real number. That potential function is phi, such that if any player unilaterally deviated, so here I highlight that player I unilaterally deviated from AI to AI prime. And by unilateral deviating, what I mean is that everybody else stayed fixed. So here A minus I denotes the collection of every player other than I. So if one player unilaterally deviated, say player I, the payoff gain, or the gain in cost or the loss in cost that that player experiences is equal to the gain or the loss in the potential function. So notice that on the left side of this equal sign, we have something that's player specific. On the right side, we have something that's not player specific. And this has to hold for all action profiles A, any agent I, and any variation AI prime. Okay, so a game is a potential game if such a function phi exists. Okay. And so once again, recall from our example that we talked about, it says, you know, if our goal was to design something where you know, Nash equilibrium, you know, the example that we dealt with before said, let's just focus on guaranteeing the existence of Nash equilibrium, the efficiency. We weren't able to do that. If we embedded a new objective to guarantee the existence, efficiency, and that the game was a potential game, that's still unattainable. Okay, that would make it even more challenging. So once again, the framework's not rich enough to deal with these design challenges and objectives. So here's the general idea about state-based games, and then we'll go into it in more detail as we proceed. So once again, the Markov games is a highly complex set of games. This is a very simplistic version of it where we have myopic players and static equilibrium concepts. And here's kind of how the game proceeds. Okay, and then we'll talk about the formalities later. Is there some state at time t, call that state x of t. At that instant, each player myopically and independently selects some form of an action. So here, agent I selects an action at time t based on certain degrees of information that the agent access to. What's the current state x of t? And then what are all the previous states and previous action profiles? Let's imagine he has that level of generality. So he's not projecting potentially of where the state is going to go. All that he's looking at, here's what the state is today. That state's going to influence my decision, and maybe I use past information to try and model what the other agents are going to do today. So one example would be maybe like a myopic Cournot adjustment process or a better reply process. So here, agent I at time t just selects the action which minimizes his cost at time t, given his belief that everybody else stays fixed. Okay. That's one idea of a potential control or a learning algorithm. There could be many others. Okay. At time t, then, after each agent selected their action AIT, agent I receives a cost, which is a function of what was the state x of t and what was the joint actions A of t. And then at time t, the state gets updated. At time t plus 1, the state gets updated and the process is repeated. Okay. So here the key is what we're going to be doing is focusing on myopic agents. And once again, why is so here, agents aren't trying to project long-term what is going to happen with the state, how are they going to influence the state. They're not worried about that. The state at time t is the state at time t, and I'm just going to worry about optimizing my cost today. Now, why is this? So this need not be reasonable in a social science perspective, but in an engineering system where these agents are programmable components, the objective that they try and optimize and how they try and optimize is a programming choice, does not necessarily have to follow what's natural or what should be done in an engineering or in a social science perspective. Okay. Okay, so that's the general feel of what a repeated game looks like. Notice that if our state space consisted of just a single state, then this boils down to exactly just a normal form game. So we have to talk about, well, what could an equilibrium, or how we're going to try and extend the definition of Nash equilibrium and potential games over to this realm. Was there a question? Okay, silence is no. Okay, so to do that, so all that we're going to try and do is just replicate what a pure Nash equilibrium is and replicate what a pure Nash, or what a potential game is. We're going to try and extend that over to this augmented game where we have a state space. Okay. So first, we're going to talk about this idea of recurrent state equilibrium. And before we can do that, just think about the following. Suppose that we played a particular action, A naught, and we're going to play that action for all instances of time from this day forward. Okay. Well, what this would do is just generate a trajectory of states. Okay, this would generate state 1, state 2, state 3, state 4, and state 5, where each state is just generated to the new state as a function of the old state and still A0 because we're playing A0. Okay, so we're going to call this an action invariant state trajectory. So once again, if we're at a particular action, A naught, where could the state go? Okay, and so here's our first attempt at extending the definition of pure Nash equilibrium over to state-based games. Okay, and we're going to say the following. We're going to say a state action pair, X naught, A naught, is a recurrent state equilibrium if two conditions are satisfied. So the first condition is just the natural, the immediate extension of Nash equilibrium domain. It says wherever the state goes, no player has a unilateral incentive to deviate from A naught. Okay, what does that mean? The cost of agent I for some state X given the action profile A naught is as good as the cost would be for if he did some optimization over his actions AI given his belief that everybody else stays fixed. So what does this mean is that irrespective of where the state goes, a myopic player never has a unilateral incentive to deviate. Okay, so that's the first extension. So note that once again, as if our state space was just a singleton, this is just the definition of Nash equilibrium. Okay. The second condition says the following. It's that, well, if it's a recurrent state equilibrium, we should have some degree of recurrence in our state space. That just means X naught will emerge at some point in the future. Okay, so these are the two conditions. Once again, this is just an extension of pure Nash equilibrium to a state-based realm, right? Once again, the first one says, irrespective of where the state goes, no single player in a myopic sense has a unilateral incentive to deviate. And the second condition just says, well, that state will eventually come back. Okay. And much like Nash equilibrium represent recurrent classes of the Cournot adjustment process, recurrent state equilibrium also represent recurrent classes of this process. Okay. So secondly, let's talk about an extension of state-based potential games, and I'll follow up why we care about this stuff. So a state-based potential game is if there exists now a potential function, so the potential function now is state-dependent. So before in the original definition of potential game, a potential was just a function from the joint action profiles to the real numbers. Now it's a function from the Cartesian product of the state space and the joint action profiles to the real numbers. So it's a state-based potential game if such a function exists that satisfies two properties. Number one is the usual condition. Unilateral deviations are aligned with the potential function. What does align mean? That the payoff or the cost gain or loss that an agent experiences by unilaterally deviating is precisely equal to the difference in the potential function across those two profiles. Okay. Now the second condition is something that we're going to introduce new. It's that the potential function is non-increasing along any action invariant trajectory. So what do we get? We get a degree of monotonicity when everybody stays put. Okay. So if we play some action A today and the state is X, the new state is X prime. If we continue to play A, the potential evaluated over those two variables has to be less than or equal to the potential function evaluated over the original two variables. Okay, so that we get a degree of monotonicity in an action invariant state trajectory. Okay, so this is once again just one potential way to extend potential games to this realm. We have to account for two things. Unilateral deviations are aligned, and what happens to this as the state evolves.
Yes, do you have an example?
We'll go into a detailed example. Okay, so why do we care about this? Is first of all, is if we have any state-based potential game, it's fairly easy to show that a recurrent state equilibrium automatically exists. So much like in a potential game, a pure Nash equilibrium exists. Here, when we're in a state-based potential game, we get the fact that a recurrent state equilibrium exists. And then the other thing that we have nice is in potential games, we know that in potential games, that structure can be exploited in distributed learning to provide convergence to a Nash equilibrium. So here we get that, in some sense, we get that the same structure is there to be exploited. And so, for example, many learning algorithms for potential games also guarantee convergence results for space-based potential games. In particular, for example, gradient play, log linear learning, finite memory, better reply processes, all these can be proved to converge to recurrent state equilibrium in any state-based potential game. Okay? And the last one is the key, the finite memory, better reply process. We talked about robustness before in potential games. And so what Young did, I think in 2004, was he introduced something called a finite memory, better reply process. And basically, this classified virtually any decision-making rule within that in which agents trying to improve their payoff. So it's some form of a metric for how do agents process some memory to go forward, and it's very, very general. Anything will fit in that. And so what this means is, so in potential games, any finite memory, better reply process converges to an equilibrium. That means that even in situations where agents are corrupted with delays in information or you name it, asynchronous clock rates, we still in some sense get that convergence. And so it turns out that state-based potential games also possess that same property. Any finite better reply process also converges to a recurrent state equilibrium. So in some standpoint, if I have a state-based potential game, getting to an equilibrium is relatively straightforward.
But users are always myopic, right?
Users are always myopic, so they're not. But let's we'll delve into that. Right now, all that we've talked about is here's a class of games and here's a class of equilibrium. It's easy to get that to that class of equilibrium in this class of games, whether that's from myopic behavior or non-myopic behavior. It doesn't matter. It's just easy to get there. Okay, much like in potential games, getting to a Nash equilibrium. Okay. So here, the difference between Markov games, between the classical, is Markov games have been perpetually interested in finding something called stationary strategies, which are policies which map states to actions, such that policies form an equilibrium. Here, we're focusing on a far simpler equilibrium. So let's revisit the objective that we had before. But let's now think about recasting our objective in terms of recurrent state equilibrium optimal solutions. So recall what we had before is we had some form of a system level objective function C. We had some form of a desired interaction graph. So then once again, these were our locality constraints. But now our goal, our revised goal is, well, can we design cost functions in the state-based realm, right? So now what is a cost function able to depend on? Some state variable xj, which is local to agent j, and the action of agent j, where I'm only able to depend on this neighbors. So the Cartesian product of my state and my action of all my, so the cost function of any agent is able to depend on the state and the action of all its neighbors, okay, but nothing further. So is it possible to design cost functions now in this augmented realm such that recurrent state equilibrium and optimal solutions were equivalent? Okay, so once again, we weren't able to do that in the original setting, right? We weren't able to do that in the non-state-based realm, in just the framework of normal form games, and we had a counterexample that showed that. But in this state-based realm, can we exploit this additional state variable to get this equivalence? Okay, and it turns out that we can. So once again, here's the flavor of our design. Is what we're going to do is we're going to introduce the state as an estimation parameter, and then we'll talk about what this means at the end of it. But once again, we're not specifying an algorithm. All that we're specifying is objective functions for the individual agents such that all equilibrium associated that, and here the equilibrium we're focused on is recurrent state equilibrium, coincide with optimal solutions. And we're doing this in such a way, right, and why we're setting it up like this is, well, if we can do this, if we can achieve this objective, how the agents actually get to the equilibrium is trivial, right, and need not apply any structure. So we get this robustness element for free. Okay, so once again, here's the components of our state, and the flavors. What we're going to do is introduce these state variables as estimation parameters. So the first component is we have the set of agents. That remains consistent with what we had before. The new component is now we have the state space X. So a state at time t, or a state at any instance of time, or state is going to be represented by a tuple of local state variables, x1 through xn, where the state of any agent consists of the following elements. The state of agent I consists of, well, what's agent I's value? And that's vi. And then it'll also include what's an estimation for the value of all the other agents in the network. Okay? So E subscript I superscript 1 is agent I's estimate of the value of agent 1. Okay? Note this need not equal the value of agent 1, it's just an estimate for the agent. Okay? Likewise, EIN is the estimate of agent I for the value of agent N. So here the subscripts will always denote what agent are we in reference to. The superscript will be what is, in some sense, who is he trying to estimate? What is this trying to estimate? Okay? So that's the set of local state variables. Each agent has a local state variable. That local state variable consists of what's my value and what's my estimation for all the other agents' values. Now we have to talk about actions. So here we're going to talk about two types of actions for an individual player. An individual player is going to be able to change his value, and that change is going to be VI hat. So VI hat is going to indicate how much do I want to change my value. And the second tuple of terms is just how do I want to change my estimation terms. And changing my estimation terms, in some sense, will be reflected of passing estimation. So think of my estimation for agent K as some sum of money. I can give and receive money from my neighbors. Okay. So here, E hat I arrow J K, try not to get, that's the estimation about agent K that agent I is sending to agent J. So I view, so imagine I'm agent I view that the estimation of agent K is, let's say, 10. I view that his value is 10. That's my estimate. I can pass 1 unit to any one of my neighbors, or I can pass 2 units to any one of my neighbors. Okay? Key is I can only pass to my neighbors. Okay? So that's the two actions that we're going to allow. Is we're going to allow agents to change their value and also agents to change their estimation terms. Okay? The next thing that we'll focus on, well, given that we made a decision, how does the state evolve? And it's going to evolve in the very natural way. So first of all, my local, how does my local value update? Well, if my value was 10 and I changed it, I raised it by 1, my new value is 11. So what does that mean is my new value is just my old value plus how I chose to change it. Okay, so that's the first term. That's the local value update. Local estimates follows a similar flavor. My estimation for agent K is my old estimation minus how much estimate did I pass away plus how much estimate did I receive from my neighbors. Okay, so there's some form of a balance going on. Okay. So once again, my new value is my old value plus however I changed. My new estimation is my old estimation minus how much did I pass away plus how much did I receive. Mind you, I think it's important to point out what we're doing is allowing agents to evaluate what they should do or what they could do. Right? This just says if they make an action, here's what happens. It's not telling an agent here's how you make an action. And that's a distinction that I'll continually get to, that I'll continue to reassert.
So you haven't specified what V hat I is, basically.
Sorry.
So you haven't said how you determine your new V hat I.
I haven't said it at all. I just said that.
I mean,
that was my point.
Yeah.
Right. Regardless of how. So once again, is we're talking about molding equilibrium. Mm-hmm. When we talk about equilibrium, these are equilibrium conditions. How we get to an equilibrium is how A is generated. Mm-hmm. Right. It's how actions are generated. That's a different question. Right? And the idea is that if we can get a potential game structure, right, we can talk about equilibrium of potential games without talking about learning algorithms that find us to equilibrium.
Sure.
I'm doing the same thing here, just in a different realm. Mm-hmm. If agents make this decision, I'm specifying what happens to the state. And then we'll argue that how agents make decisions, regardless of how they make decisions, we're going to get to a recurrent state equilibrium.
Sure.
Okay. Okay, so that's the local estimate update. It just follows that natural form. And we have one small caveat in here is that each agent maintains an estimate of themselves. And in this case, we have something that follows the similar term, but we have the addition of this one extra term N of VI hat, which just means if I change my value, I need to introduce this additional term for how I introduce my, how I change my estimate of myself. Okay, and all that this state updates are used to do is preserve a degree of conservation. So for example, if the initial estimates satisfy this equation, this top equation, if the initial estimates at time 0 satisfy some relation to the true initial values at time 0, and note it's relatively easy to satisfy this condition, then regardless of what happens, irrespective of the actions that agent takes, we preserve this relationship throughout. Okay? So regardless of how agents make decisions, regardless of what decisions they make, we preserve that, the state dynamics preserve this relationship between the actual value and the estimation terms. Okay? So in here, what we're now lastly is what we talked about is designing these local cost functions. What does it mean for something to be local? Is that the cost of agent I can only depend on the states and the actions of me and my neighbors. And so here's the cost function that we're going to consider. The cost of agent I for a state A and an action profile A can be expressed as the sum of two components. The first is the system cost component. So what's that? It says, well, what I'm going to do is I'm going to sum over all my neighbors, and I'm going to evaluate the system cost at my neighbors, at each one of my neighbors' estimation terms. Okay? So that's this first component, is that I'm, the first part of my cost is say I'm just going to sum over what's the system cost for each one of my neighbors' profile of estimation terms. Okay? Note that that depends only on local information. Okay? All that depends on, that first component depends on, is what are the estimation terms of my neighbors. Okay. Now the second component relates to the estimation terms, and basically it takes on this form here that just basically, in some sense, penalizes is how far are how far is my estimation terms from my neighbor's estimation terms. And we do a summation, but that's the essence of what this captures. So if you can see kind of what's going on here is that agent or the JIC is trying to align the cost function of agent I with the system cost. The second component of these cost functions are trying to get some form of consensus on estimation terms. We would like it to be that everyone is consistent in their beliefs about what's going on in the system. Okay? But note that irrespective of what the interpretation is these cost functions only depend on local information. Right? An agent I can evaluate his cost for a given state X and an action profile A using only state variables of his neighbors and the action of his neighbors. Okay. So here's the first theorem that we have is, first of all, it turns out that this game is a state-based potential game, and there's the potential function. Okay. So mind you that the existence of the potential function is what's important, not what the potential function looks like. Okay. So what this potential function means is that, think about this, is that a recurrent state equilibrium exists, and that basically any distributed learning process will find a recurrent state equilibrium. Okay, that's what this gives us. Here's the precise structure, but the structure isn't what's important. Okay, we get the existence of a recurrent state equilibrium, and we get dynamics that'll get us there. So once, so the second theorem is the characterization. It says, well, an action state pairs a recurrent state equilibrium if and only if the following conditions are satisfied. First of all, the value profile is optimal. So we solved the optimization problem up from the get-go. Everybody's estimation terms is in fact accurate. So my agent I's estimate of the value of agent K actually turns out to be V of K. The change in the values are 0, and these estimation terms, or the change in estimation terms, satisfies this. What goes out comes in. So we get a balance of 0 on that. Okay. So what does this mean? It means that, once again, is the only recurrent state equilibrium that exists satisfy these conditions. What does this mean is that all recurrent state equilibrium represent optimal solutions to our original optimization problem. So what we weren't able to do using the framework of just potential games and normal form and strategic form games, we are able to do using the framework of. So the objectives that we set forth is, can we design utility functions such that Nash equilibrium exists, Nash equilibrium are optimal, and we have an underlying game structure that can be exploited in distributed learning. We weren't able to achieve those objectives using the framework of normal form games. We are able to achieve those objectives in the framework of state-based games. Okay. So real quick, and I'll only spend a second on this, or a couple seconds on this, is, the example that we talked about introduced had linear coupled constraints into it. The sum of the agent's values needed to be equal, right? Needed to stay fixed. And so here we can expand our setup ever so slightly, expand our notion of cost functions to actually get the desired equivalence between recurrent state equilibrium and optimal solutions for this state space world as well. And so the flavor of the design is the following: is, well, let me just take my system level objective function and let me use penalty functions to relax these constraints. And so here's the penalty functions that we're introducing, where mu is just a trade-off parameter. And now let me kind of proceed in a very similar but systematic fashion. So now here I'm going to introduce, here the state of agent I is now consists of his true value, his estimate for everybody else, and also his estimate for the constraint violations. What's a constraint violation? CI is just the estimate of C, which is my constraint here. I should have used another variable besides C, but C minus AV. So it's just an estimate for my constraint violation. And here, just skipping along, proceeding in the same fashion, the actions take on the same structure, the state transitions take on the same structure. But here now for cost functions, is we're just going to integrate or one additional term into the cost functions. So JIFC and JIV are exactly the same by its floor. But now we just introduced the third component into our objective functions that captures this idea of these constraint variables. How have we violated the constraint, or do we think we're violating the constraint, and we've received some form of a penalty of that? Okay. So once again, we had some form of a coupled constraint added to our process. What did we do? We introduced a new component to our cost functions that were just in an additive fashion. So you see here we had one, then we had another, then we had another. It's just introduced in an additive fashion, and it roughly takes on the same form that we had before. Okay. And so in this realm, what are we able to show is, once again, the game is still a state-based potential game. The potential function looks like the old potential function plus some new component that's related to this new element on the cost functions that we introduced. And once again, so we have a state-based potential game. Once again, the structure is not important. What does this give us? This gives us the fact that a recurrent state equilibrium exists and that we have learning algorithms that'll get us there. And that's relatively easy to get there. So in response to Srinivas's previous, how A's are generated, it really doesn't matter. As long as A's are generated according to any form of a reasonable process, where I'm going to put reasonable in quotes, we'll get there. Okay. What do we get also? The second part of the theorem shows that we get the equivalence between recurrent state equilibrium and optimal solutions of this problem. So here, the value profile optimizes that relaxed version of the constraint. Our estimation, our terms are accurate, and our estimation of the constraint violations are also accurate. Our change in our values satisfy this, and our change in our estimation profile and constraint estimation profile is consistent. But the key here is that what we have is that even in this addition of coupled constraints, the same machinery did the job. Is we were able to design utility functions or cost functions in such a way that we preserve, that we attain this equivalence between recurrent state equilibrium and optimal solutions. And since we dealt in the realm of state-based potential games, the idea of how we get to a recurrent state equilibrium, that's a trivial process after that. Okay. So let's go back to our example before. As once again, here's the problem of average consensus. We want to solve this optimization problem, which fits into the realm that we were dealing with, that we were talking about before. Once again, our admissible controllers, here's our admissibility constraint, is that the value of agent T can only depend on information about his neighbors at some instance of time. So here's an approach, a very systematic approach, is model it as a state-based game. Apply any learning algorithm that guarantees convergence to a recurrent state equilibrium for state-based potential games. Gradient play is one such algorithm. And we get convergence to the optimal solution. So here's the plot on the right. So the plot on the left is a three-dimensional plot that kind of shows how the values are evolving as a function of time, where time is labeled on the z-axis. So you see that all the values converge together at about at the average. The plot on the right is something that I deem is more important. So here what we see is, we talked about that this potential function could be broken down into different components, could be thought of in different components. We saw that the potential function was an addition of several terms. And so here we can think about the terms in the two parts. Is we can think about one as, The black indicates is how far are estimations away from reality. And the blue could talk about, well, how well is our current values doing? Okay, so we can decompose it in these two structures. And what this shows is the fact that the black line is high means that there's, in some sense, the black line being above 0 means that, in some sense point, is our constraints, our estimations are never accurate. This shows that there's a major inconsistency between our actual estimations of the values of other players and their actual values. But what this also shows is the blue line going down says, in spite of that, even though we are responding to poor estimates, we are still achieving a desirable behavior. And so notice that the black line is not monotonically decreasing, and it's not monotonically decreasing because that's not the potential function. The red line is the potential function. We see that the red line is monotonically decreasing according to this gradient play process. Okay. And so this is kind of the last slide is just an overview. It's just kind of highlighting some main questions that I'm pursuing, and I think that are a variety of open questions in the area. This idea of thinking about using game theory for engineering systems introduces a new dimension to game theory that hasn't been rigorously explored. And the idea is, well, this idea of designing agent-objective functions is a relatively new phenomenon. It's been studied in the social sciences in mechanism design and cost-sharing problems, but those problems are fundamentally different, have a different structure and different constraint sets than we would be looking at from an engineering perspective. And so this begs a lot of questions. As we're interested in performance, how can we design agent-objective functions with the idea of that using them as the segue into control policies? You know, and we could ask a variety of questions from, you know, how do we design, you know, what is attainable and not attainable using the framework of normal form games? So what are the limits? What is the best way to extend it? How can we optimize the price of anarchy? One way of casting the results that we had today is that using state-based games is we were able to ensure that the price of anarchy was 1, meaning that any Nash equilibrium was optimal. In general, we can't do that. So, you know, most of the work on price of anarchy has really focused on an analytical side of things, meaning that, you know, given cost functions, given a system-level objective function, what is the inefficiency associated with Nash equilibrium, you know, according to that system-level objective. But here, everything is given. So price of anarchy is very much analytical in nature. We're interested in more the design question of price of anarchy, is how can you design cost functions to optimize the price of anarchy? What would those look like? What would those not look like? And then, you know, since we are dealing with engineering systems, is we have the ability to introduce communication in the system. What does that mean? That means allow us to enrich the set of control policies that an agent is going to do by the use of a communication network. And so that's kind of what we took advantage of today. But in some sense, what's the proper way to introduce communication into a game setup, how to exploit communication, those remain, I think, very open and interesting research directions. And with that, I'll conclude. And once again, I want to thank Srinivas for inviting me to give this webinar.